Hello everyone, welcome to Reactify Labs. Today we will talk about an algorithm called Raft. So what is Raft? Raft is basically a consensus algorithm. Means if multiple nodes need to agree on what the value of a particular data should be, so there will be a democratic process called voting, and depending on the vote, one value may or may not be written on the for a particular key or a particular node, anything. So basically we can think of it as another way or alternative to the topic that we had studied. It was called quorum, right? Quorum, and in that we also covered sloppy quorum. So there also the voting was done, so here also some voting is done, and this is the best way to start to get some idea about what this algorithm is going to be and how it works and what are the benefits and drawbacks of this and why this is used. So let's start. So raft is basically a consensus algorithm. So it's a consensus algorithm used in distributed systems to ensure all nodes agree on the same state. To ensure all nodes agree on the same state. It simplifies the complexities of consensus. It simplifies the complexities of consensus and is easier to understand compared to other algorithms. Compared to other algorithms like Paxos. Okay, so there is some algorithm called Paxos. We don't know about it yet. Means I have not made a video on this. I'll probably make some in future if it's required, or maybe not also. Okay, so that's for the future. Leave it aside. Let's see what are the key components of Raft. So the key components is first is leader election. So Raft uses a leader follower model where one node serves as the leader. If the leader fails, a new leader is elected through a democratic process involving all nodes. And then there will be a log replication. Each node in a Raft cluster maintains a log of commands that have been agreed upon. Logs are replicated across all nodes to ensure consistency. And then there will be heartbeats. So the leader sends periodic heartbeats to followers to maintain its leadership status. If a follower doesn't receive a heartbeat for a certain period, it initiates a new leader election. Okay, so let me explain what happened here. So there will be multiple nodes. Okay, each node will have its own log because this is a distributed system. So each will have its own copy, and then each needs to be updated, so they will all share their logs. Okay, they will all exchange their logs so that everyone has all the copies of all the nodes, even though the writing of logs will happen in a distributed manner. Means duplication will not be there. Okay, so let's say one region, America region writes on this log, India region writes on this log, Europe writes on this, Africa writes on this, Australia writes on this, something like this happens. Okay, so this is what the distributed system is. Okay, different nodes take logs from different places and they share among each other. Okay, which makes the system scalable. So this is the core concept of distributed system. So I'm not going to throw more lights on it. This should be clear up to now. If you are still having some doubts, please go watch the previous videos in which I've explained it all in detail. Okay. So there are different logs and there will be a leader. Let's say this is a leader. So if one is a leader, then others are a follower. Okay, one leader is randomly selected and then others are a follower. And whatever the leader says, others will vote on that. And then depending on the voting, how many people agree, that decision will be carried forward or not. And this leader, okay, leader election done, log replication done, and then heartbeats. So this leader constantly sends heartbeats to everybody and keeps on telling everybody that, see, I am alive, I am alive, I am alive. Okay. And let's say for some reason this node does not receive the heartbeat. Okay, so this node assumes that the leader might be dead, and so it initiates a new leader election process. Okay, so that's what heartbeat is all about. Heartbeat helps leaders convey the information to everyone that I am alive. Okay, so now that we have discussed the components, let's talk about the leader election process. Leader election. In Raft, leader election is triggered when a follower hasn't received a heartbeat from the leader for a certain period. It means election timeout. So, any follower can trigger the leader election process if it does not receive a heartbeat. During an election, nodes request votes from others, and the node that receives votes from a majority becomes a new leader. This process ensures that there is always a leader in Raft cluster to coordinate log replication. Okay. So this leader, this node, let's say, starts the leader election process. So it tells everyone that, see, I am the leader. If every node agrees that, okay, this node is going to be the leader, then it will become the leader. It is possible that two nodes at the same time detect that the leader is down and they both initiate that this says I am the leader, this says I am the leader. So other nodes will vote on that, and depending on the vote count, a new leader will be elected. So let's say this one got elected and this is down, then again somebody else will also start, and then so every time there will be a new leader. As soon as the leader is down, there will be a new leader. Even if the leader is not down, still there can be a new leader because the leader failed to convey its availability to everyone else in the node. Okay. Next, let's talk about log replication. Log replication. So first one is log entry structure. Each log entry in Raft contains a term number and a command. The term number is used to identify the leader for that entry, and the command is the operation to be executed. Log entries are appended to the log and replicated across all nodes in the cluster. Okay. So basically, it's very straightforward. Different nodes will have different logs. Okay. Each log will have a term number and a command. So term number, each log will have a term number and command. Okay. Term number is used to identify the leader for that entry, and the command is the operation to be executed. Okay. So the term number is nothing. It's just the an identity of the leader for one particular entry. Who was the leader? Okay. That's it. And the command is the operation to be executed, the operation which we need to execute. Let's say write or read or change or something else. Okay. So that's all about the log entry structure, and what it does is it guarantees consistency. So Raft ensures that all logs are consistent across nodes by using a process called log replication. Once a log entry is committed by a majority of nodes, it is considered final and will not be changed. Okay. So the log entry has to be committed so that it's final. Okay. Before being committed, whatever stage it is in can be rolled back, but after committing, nothing rollback happens. Okay. Next, let's talk about heartbeats and timeouts. heartbeats and timeouts. So first talk about heartbeat mechanism. The leader sends periodic heartbeats to all followers to inform them that it is still alive and to maintain its leadership status. Followers use these heartbeats to reset their election timeouts. If a follower does not receive a heartbeat within its timeout period, it assumes the leader has failed and starts a new election. So here comes the timeout also. So there are different nodes. Leader keeps on sending everybody about its status, let's say 100 seconds. And let's say for this node, these nodes 50 seconds have passed. And it receives it now. So as soon as it receives it, it resets it to 0 and again starts the timer. Everybody. Okay. And for some reason, if it does not receive and it becomes 100, then a new leader election process will be started. Okay. So this is the heartbeat mechanism, and this was the role of timeout. So let's talk about timeouts also. So Raft uses randomized election timeouts to prevent multiple nodes from starting an election simultaneously. The randomized timeouts ensure that only one node becomes the leader, reducing the likelihood of split votes and maintaining system stability. It means different nodes have different election timeouts, okay? And each node need to wait for the specific timeout allocated to them before they start their own leader election process, okay? But why it is done? It is done so that no two leaders or different leaders should not start it at the same time. But then you will ask, how will it be possible that different leaders start the election at the same time? As I told you about a collision when two leaders start at the same time. So that might happen. Let's say there is an election time. This was given 100, this was given 50 seconds. And this one, when there was a new leader, there was an existing leader. This one failed to receive the update. Okay, after 50 seconds, after almost 50 seconds, this one failed to receive the update and this one received the update. So this one reset timer to 0. Now it also has to go 50 seconds. It also has to go 50 seconds. It is possible that both of them did not receive it next time and both of them start the leader election process simultaneously, right? So these are the cases which can happen. So that's why timeouts are used. Now let's talk about something called safety features in Raft. So it's safety features. First one is term-based approach. Raft operates in terms, with each term representing a unique period of time during which a single leader is elected. Using terms helps Raft distinguish between outdated and current information, ensuring that only the most recent log entries are committed. Okay. And next one is commitment mechanism. Raft ensures that a log entry is committed only if it has been replicated on a majority of nodes. This ensures that the committed log entries are durable and will not be lost even if a minority of nodes fail. Now let's talk about the fault tolerance. If it's a distributed system, it's a distributed system algorithm that it must provide some fault tolerance mechanism. So first one is leader failure. If a leader fails, Raft uses its leader election mechanism to elect a new leader. This ensures that there is always a leader in the cluster to coordinate log replication. And then there will be follower failure. If a follower fails or becomes disconnected from the cluster, it will not receive heartbeats from the leader and will start a new election to elect a new leader. This fault tolerance mechanism ensures that Raft can continue to operate even if some nodes in the cluster fail. Okay. Let's talk about some of the use cases of Raft. First one is distributed databases. Anything which has the name distributed can use Raft algorithm. Raft is widely used in distributed databases such as CockroachDB and TIDB to maintain consistency and reliability across nodes. It ensures that all nodes agree on the order of operations, preventing data inconsistencies. Next, Cloud services. As you know, cloud services are usually distributed. So, cloud platforms like Kubernetes and Docker Swarm use Raft for leader election and coordination among nodes. Raft ensures that distributed systems running on these platforms remain available and consistent. Let's talk about the difference between Raft and other consensus algorithms and why Raft is good. Raft versus other consensus algorithms. So Raft is favored for its simplicity and understandability compared to Paxos, which is known for its complexity. Unlike Paxos, Raft uses a leader-based approach, making it easier to implement and reason about. So the advantages of Raft is Raft's leader-based design simplifies fault tolerance and recovery compared to the complex quorum-based approaches. Raft leader election and log replication mechanisms are more straightforward, making it easier to implement and maintain. Okay. Now let's talk about some of the real world examples. Real world examples. First one is etcd. So etcd is a distributed key value store used in Kubernetes. It uses Raft for leader election and consensus. Raft ensures that all Kubernetes nodes agree on the current state of the cluster, ensuring reliability and consistency. Next is Consul. Consul is a service discovery and configuration system which uses Raft for leader election and consensus among nodes. Raft ensures that all nodes in Consul agree on the state of the service discovery catalog, ensuring reliability and consistency. So, as we have talked about all the good things about Raft, let's talk about some of the challenges. Because if it's distributed system, obviously it will have some challenges which we need to address while implementing it, right? So first one is network partitions. Raft can face challenges in the presence of network partitions where nodes are isolated from each other. Careful design and implementation are required to handle network partitions without compromising the consistency and availability of the system. So network partition will be there. If there is a distributed system, there will be different nodes. What they will usually do is they will communicate over the network, okay, using something called RPC. So there may be network partitions and you need to handle such cases. What happens in case of network partitions? How your data consistency or data reliability is maintained in case of network partitions, okay? And next is implementation overhead. While Raft is simpler than other consensus algorithms, it still requires careful implementation to ensure correctness and efficiency. Developers need to understand Raft's principles and design considerations to effectively implement it in distributed systems. Okay, so this completes the uh, discussion about Raft, and I believe I have covered most of the things. And yep, I hope this gives you a good idea about what Raft is, what are the key components of the Raft, what's leader election, what's heartbeat, what's timeout, why Raft is good, what are the real life use cases where Raft might be used, and why it is good as compared to other algorithms. And yep, that's it. Thank you for watching. Please remember to like, share, and subscribe. I will see you in the next one.